We have an example in this slide, and we will see the effect of nonlinearity when we use Taylor series. In this example, we have a function, as you can see here, x to the power m, and with the increase of m from 1 to higher numbers, the function becomes from linear to nonlinear. There is a transition. So we will investigate how the Taylor series expansion will predict these. So basically we will use the first Taylor series. Actually it says first order Taylor series, using that to predict this function. So let's write down the first Taylor series. So it is for n equals 1, Taylor expansion, and we know that the expansion is fxi plus 1 is equivalent to, and this is 4, fxi plus the derivative. So because we need derivative here, let me write it down first. The derivative of xi times h plus r1. So when we write r1, this is exact. If we truncate from here, it will be tilde on top of this. But for now, this is fine. And let's find the derivative. If the function is this, then the derivative is m times x m minus 1. And simply we can write this over here to the derivative. Let me erase this and write down the derivative so that we can continue with it. M xi m minus 1, which is the derivative. Let's write this way, fxi prime. And we know that the truncation is from here, from after the first order. That's why R1 will include the second order and the other terms. So that we can write down R1 is equivalent to the second order derivative divided by 2 factorial, and h square, the step size, is also increasing in power, and the third derivative xi divided by 3 h cube, and it goes this way. And now we have the Taylor expansion with the remainder term or the truncation term, and we can now we will use two problems here. First, we will investigate the effect of the power m, this m, and see if the first order Taylor expansion predict these well enough or not. Let's say the first step or the first case, examine how approximation behaves as m increases. The first case is this. So let's start with m equals 1. If m equals 1, we know that this fx is just x because m is 1. Then we can simply use this function to predict. Let's say we will predict x equals 2 by considering the previous value as x equals 1. That's why we will find f1, and if we write 1 here, it is, as you see, 1. Similarly, if we write 2 as x, it is 2. And this is the exact value or true value, because we calculated it using the exact function. Now let's use the prediction. That means the first order Taylor series. F2, and I will write tilde by skipping remainder term. So simply I will take this function here, use as xi plus 1 is 2 and xi is 1. This is equivalent to f1 plus m is 1 times xi is 1 to the power m minus 1, which is over here. I'm writing this 1 minus 1 times h is, you can see the difference is between 2 and 1, or sorry, the x's, xi plus 1 minus xi is 1 actually. That's why h is also 1. And we know that f1 is 1 over here. So this is simply, the result is 2. And you can see that the true value for f2 is 2 and the predicted value for 2 is again 2. So these are the same. That means there is no error actually. And we can see the same for, by calculating R1. Let's write R1. R1 says we need to have the second derivative. And the second derivative, if the first derivative is just, so our function is f x equals x. The first derivative is 1. The second derivative is 0. That means the third derivative is also 0. And onwards, all the derivatives are 0. Which means if we write these down here, all the terms are 0. So that shows that our R1 is 0. Because all the derivatives with the second derivative are 0 for m equals 1. So with this information, we see that the remainder term or the truncation is 0, error is 0, which shows that the first order Taylor series has the exact value for this function, which is a linear function. So you can see here in the graph, this linear function is fx is just x, and this is simply the expected result because the Taylor series always gives exact result for the same order of polynomial. And we see the same exact thing here. Okay, so let's move on to m equals 2 then. Then fx is x squared. Then we will do the same steps. We want to find f2. Actually, let's find f1 as well because that's necessary. It's again 1. When we put 1 here, it's again 1 to the square 2, and it's just 1. And f2 is 2 to the 2 square, then it is 4. This is the true value again. And on the graph here, it's actually for 2. The function result is for this value. And for m equals 1, the function is 2, the exact values. So let's continue and use the Taylor series to find f2 with f1 plus, here now m is 2 and here 2 as well. Let me write it down. 2 times xi is again 1 to the power 2 minus 1 times h is again 1. I'm not writing R1 because I used tilde. That means this is the prediction by truncating here. So f1 is also 1, for this case 2 here. Then the result is 3, you can see. And if we calculate R1, it is actually the second derivative, you can see here, and the first derivative was 2y, because let me write it down. So the first derivative is just 2x, while the second derivative is just 2, and the third derivative is just 0. So in the R1, after the third derivative, the terms are 0, but the first one, f2, the second derivative is 2, and I will write 2 here. 2 divided by 2 is 1, h is 1 as well, R1 becomes 1. So basically here, 2 divided by 2 times 1 square plus 0 equals 1. Then you can see, let me erase these. And the summation of the estimated f2 and the remainder term should be the exact value, because according to this formulation. So 3 plus 1 is equals to 4. And you can see the prediction is not exactly the true value. There is a discrepancy. The reason of it is that we are trying to estimate a second order function using a first order Taylor series. That's why now there is a discrepancy, because it is still thinking that this is a linear function by estimating this. And if we try to draw the function, we will see at 2 it is 3. We can just put it here, the prediction, and in 1 it is 1, and it's just approaching like this. So this is actually f tilde x for x2 for this function, and this is just linear prediction, so there's a discrepancy. As you can see, this is the discrepancy, and this is 3. So we can continue on this, and let's write fm equals 3, fx equals x cubed, then f1 is 1, and f2 is 2 to the power 3, which is 16. Sorry, for this case it's 8. To the power 3 is 8. These are the true values. Let's calculate f2, and that is 1 plus, so we will check this again, 3 times 1 to the power 2, because m is 2, times 1, 2, times h is 1. Then the result is, as you can see, 4. And if we calculate R1 will now include the first derivative and the second derivative, these ones. So it's just the summation of them, and if you do this summation, you will simply see that R1 is 6 divided by 2 times 1 square plus 6 divided by 6 times 1 to the power 3 plus 0 equals 4. And you can see the difference is pretty much now, because this is a third order function and we are trying to predict it with a first order Taylor expansion. But with R1 we can complete it. 4 plus 4 is equals 8. And if we draw the graph of this, it's basically predicting like a linear function like this for this one. This is the f tilde x for this, and you can see the discrepancy. It's pretty much too much discrepancy now. And let's do this the same for m equals 4. Similarly, fx is x4, f1 is 1 again because it's just 1 to the power 4, and f2 is 16. And if we calculate the Taylor series for this, it's again a linear approximation. F1 is 1, plus m is 4 times 1 to the power 4 minus 1 times 1, and it becomes here 5 actually. And if we calculate R1, it is 11. The summation of these should be this true value. True value is this, and we predict the true value 16 as 5 with the first order approximation. The difference is getting more and more because the degree is increasing, but our Taylor series degree is the same. And the remainder term shows the increase of the truncation error. Then our function for this scenario is just for 2, it should be 5, like over here. And if we draw, it's a linear function like this. This is linear, and this is for f tilde x for this one. And you can see the discrepancy, it's too much. In other words, we see that with the increase of nonlinearity or increase of m, we see that the truncation error R1 is also increasing, and the prediction is less accurate. So this is the effect of nonlinearity when we keep the Taylor expansion degree constant as like linear, for example, here. So we finished this first step. Let's move to the second step in the next slide, in which we will investigate the step size effect, the change of h basically.